Hi guys, this time we're going to talk about integers. We're going to talk about the real number system. And we're going to talk about how integers and different types of integers all fit into that real number system. The first question I usually get is, Ms. Graham, what is a real number? Well, as of right now, a real number is any number you know about. Then usually the second question is, well, Ms. Graham, if it's the numbers I know about, that makes it sound like there are numbers that I don't know about. And that's true. There are imaginary numbers that go along with the real numbers, but we're going to leave that for when you're older. Our big concern today is going to be looking at the real numbers. And if you look over here, you have a Venn diagram of sorts that shows you the relationship between all of the types of real numbers that are out there. The first thing we do is we divide the real numbers into the irrational numbers and the rational numbers. Inside the the rational numbers, we have integers, whole numbers, and natural numbers, and they nest inside of each other. So all of the natural numbers are also whole numbers. All of the whole numbers are integers. All of the integers are rational numbers. Rational numbers are all real numbers. What we need to do, though, is go from the inside out and talk about what these numbers actually look like. So we will start right here with the natural numbers. The natural numbers are the first numbers you learned. They are the numbers you learned to count with. They're used for counting. Notice, though, 0 is not included. When you first started learning to count and you started counting on your fingers and toes, you started with 1 and kept on going. Inside the natural numbers, we have two types of natural numbers. We have prime numbers. Prime numbers happen if the number is greater than 1, and that "and" is pretty important right there. Excuse me. Its only factors are 1 in itself. In case it has been a hot minute since you talked about factors, factors are the numbers that can be multiplied together to give a larger number. So if I were interested in the number 6, well, I could multiply 1 times 6. I could multiply not 2 times 2. 2 times 3. Those are all factors of 6. But because 1 and 6 are not the only factors of 6. We also have 2 and 3 sitting over here. That makes 6 not a prime number. That actually makes 6 a composite number. It happens to be greater than 1, but it is not prime because it has factors other than 1 and itself. If you look at the number 3, the only ways to multiply numbers to get 3 are 3 times 1. Its only factors are 1 and itself, so that makes 3 a prime number. And that makes 6 a composite number. Then give you some more examples down there near the bottom. Now from the natural numbers, we graduate to whole numbers. Whole numbers are the natural numbers and 0. So we talked a minute ago about how 0 was not a natural number. Now we're going to throw it in there. We are adding 0 to create the whole numbers. Now we're going to go one step up to the integers. The integers are all of the whole numbers, so 0, 1, 2, 3, 4, 5, and up. And they're additive inverses. Now, if you are like me, you see this additive inverses term for the very first time and you think, what? That's not real helpful. The additive inverses just means the negatives of the whole numbers. So the negative version. So we're keeping 0. We have 1, 2, 3, 4, and it keeps on going. But we also have their negatives. So those are the integers. The big catch here is that you get no fractions or decimals. We can break the integers down into 2 groups. We can break them down into evens and odds. Now, let me give you a fancy definition. It says it's even if it can be written in the form 2n, where n is an integer. Otherwise, they're saying it's also the same thing if 2 is a factor. Basically, if we boil this down into normal people speak, a number is even if you can hit it when you start at 0 and count by 2s. So 2, 4, 6, 8. That's what that means. The only other option is odd. Now this says it's odd if it can be written in the form 2n minus 1, where n is an integer. So if 2 is not a factor. These are all the numbers you don't hit. So all the numbers you miss. When counting by twos. So they give you some examples. Notice in the examples that even negative numbers can be even or odd. Also notice that 0 is even. Next, we grow one set bigger to the rational numbers. The rational numbers can be written as the ratio of two integers. In case it's been a hot minute since you talked about ratios, a ratio simply looks like a fraction. So if you can write a number as a fraction with an integer on the top and an integer on the bottom, you get a rational number. A lot of the times people will stop and they'll say, but Miss Graham, you said that all of the integers were rational numbers. Yes, integers are rational numbers. If I want the integer -3, I can write that as -3 over 1. And that is an integer divided by an integer. So that gives me a rational number. Then give you some examples. 1/5, you have an integer over an integer. The other key thing to look for if you have a decimal is that the decimal form of the number will have a terminating or a repeating decimal. Sometimes that is easier to look at a non-example. If you look at these, again, 1/5 is a ratio of integers. 3.25, it stops. It doesn't have decimals that keep on going behind it. 0.81252525 keeps going. That's what the little dots mean. It keeps going the way it's written. But it has a pattern that repeats. So that pattern that repeats makes it a rational number. 0.06, remember the line on top means repeating. It's going to go over and over and over again. Since it's a repeating decimal, it still counts. Now let's look at pi. Pi is 3.14159. Add some change. There is no pattern. And so far, it is non-terminating. I would like to say it's infinite, but I don't know that we can necessarily prove that. All we can do is keep looking for the next digit. And scientists are doing that currently. They haven't gotten to the end yet. So pi is definitely not rational. Because it doesn't follow any of the behaviors that it that were demonstrated with those. So I'm going to take my little non-example right here, and I'm going to carry him down to his home. as an example of a non-repeating number. This takes us to the irrational numbers. And this says that irrational numbers are any numbers that cannot be represented as the ratio of two integers. They are usually imperfect roots, meaning that when you take a square root of a number, it's not a nice, pretty number. Here's pi that we talked about. They have non-repeating, non-terminating decimals. The other clue they give you is the square root of a prime number is irrational. So any prime number, 13, 2, 7, 11, all of those would be irrational numbers. Now, inside the real numbers, you only have two options, and there's a good picture down below. Once you join the real number club, you only have two choices. You get to become rational or irrational. Only two options. If it's not one, it has to be the other. The other thing that we need to make sure we get out of the way so that we can talk to each other is the definition of positive and negative. Positive means greater than 0, not greater than or equal to. Negative means less than 0. Again, strictly less than. There's one thing that gets left off of here, and that is the idea of trichotomy. A real number really only has three options when it comes to the sign. It is either positive, or greater than 0, negative, so less than 0, or equal to 0. Those are your only three options if you're a real number. You're either positive, you're negative, or you're 0. Here is a happy little family tree of real numbers to help you with your classification. Then we're going to go down below and look at some classifying. So, 24. Well, if I start on the inside, remember the natural numbers were the counting numbers. Well, 24 is a counting number. So it is a natural number. But because it's a natural number, it's also a whole number. Whole numbers are also integers. And integers are rational numbers. And all of the rational numbers are real numbers. So those are all of the classifications for 24. Now I need to go look at negative 12. The natural numbers were only the counting numbers, 1, 2, 3, 4, 5. Negative 12 definitely does not fit in that category. The whole numbers were just the counting numbers and 0. Well, that doesn't do a whole lot for us because we need the negatives. It wasn't until we hit the integers where we got the positive and negative whole numbers. So that is where we start. Negative 12 is an integer. It's also a rational number. And that means it's also a real number. Now I'm going to go look at 2.5. It is a decimal. So, because it's a decimal, that means we are throwing out the natural numbers, the whole numbers, and the integers. Our only two options are rational and real. Well, remember for a rational number, when we had a decimal, our decimal had to terminate or repeat. Well, there's nothing back behind the 5, so our decimal definitely terminates. That means it's rational. Because it's rational, it's also real. 2 more. 5/3 is a fraction, but I know that 5 is an integer and 3 is an integer. That means we are looking at a rational number that is also a real number. Last but not least, we have the square root of 7. Now, we had a rule right back up here that said the square root of a prime number is irrational. Remember, a prime number only has 2 factors, one in itself. Well, 7 is only equal to 1 times 7. So that makes it prime. That means that the square root of 7 is irrational, but it is real. Now it is time for you to go do a little bit of practice with the classifying in the example, and I will check those with you